All right, in this video we're going to continue solving a practice quiz on polar coordinates. So let me try to get this organized again. Every time I restart the screen capture, it kind of moves some things around, and it's really annoying, but there's nothing I can do about it. All right, so we already solved problem number one. You can get a copy of the quiz in the description, and now I'm going to move on to problem number two. So for problem number two, we got kind of a lot going on here. So what we want to do is use polar coordinates and integrals to find the area of the region determined by the solid lines and the curves in the figure to the right. So the solid lines are here, and then along this arc, and then here, and then this line right here. So it's a pretty nice polar region, except actually for this line. This line is not meant to be in polar, but we're going to do it anyway. So let's see. First thing I want to do is figure out my theta bounds, right? So this line, this radial line here is a theta, and this radial line here is a theta. So let's see what we can do with those. So let's name our curves so we can use them. So that's going to be R1, and I'm just going to say R1 is equal to 12, right? Because it's a circle with a radius of 12, so we're good with that. And then let's look for some ordered pairs. There's actually two really nice ordered pairs that we can use. So here's one, 7, 3. And if a line through the origin passes through the point 7, 3, then we actually know the angle is the inverse tangent of 3 over 7. So that's our first angle that we're going to use. So that's like theta sub 1 maybe if you were going to name them. And then we can do the same sort of thing for this other line. So that point is 3, 9, which makes this angle the inverse tangent of 9 over 3, which is 3. So far so good. Now let's deal with this line that shouldn't really be written in polar, but we're going to do it anyway, because why not? So we got this line right here. So it goes through the point 3, 9. The slope you can just kind of count off, right? It's down 6 over 4, so simplify that, you get negative 3 halves. So I'm going to write the whole equation in point slope form. So y minus 9, negative 3 halves, the quantity x minus 3. What I like to do with these is I like to rewrite them in kind of basically standard form, but I don't really care if I have integers, and I don't care if x has a leading coefficient that's positive. So what I'm going to do is multiply through by 2 and get 2y minus 18, and then distribute the 3, negative 3x plus 9. I'm going to move the 3x over and also move the 18 over. And this is the way I prefer to rewrite a line in polar. So now I'm going to replace y with r sine theta and x with r cosine theta. So we get something that looks like this, and that equals 27. And then what we can do is I'm going to name it R2, so it's going to be 27 over, so I factored r out of both things on the left-hand side there, and we get 27 over 2 sine theta plus 3 cosine theta. And we're actually kind of ready to just finish this problem because we have the inner curve, we have the outer curve, and we know where theta starts and where theta ends. So our total area is going to be, let's see, so it's 1/2, never forget the 1/2. The integral from the bottom angle, which is arctan of 3/7, to the top angle, or as you rotate, I guess I should say, as you rotate counterclockwise, we first hit arctan of 3/7, then we hit arctan of 3, so those are the bounds there. And then it's the bigger area, so the bigger area is obtained by squaring r1, so r1 squared, and integrating, and then minus the smaller area, which we'll get by integrating r2, so that region, so it's going to be the quantity r2 of theta squared d theta. Let's use a calculator on this. So I'm going to start a new problem. And calculator, I'm going to store some things. So R1 of t, I'm going to say it's 12, which there's really no point in storing, but I'm going to do it anyway. R2 of t is our line, so 27 over 2 sine of t plus 3 cosine of t. Got that. And then our integral, so it's 1/2, the integral from arctan, so I was going to type arctan, which works, but you're probably going to do this, of 3/7 to the arctan of 3, and then it's r1 of t squared minus r2 of t squared, and then dt, and let's see what we get. We get 7791. As you can tell, I have trouble reading decimals. So approximately 33.779. And that's the area. Okay, so that's question number 2. I'm going to cut this video here, and I'll be back to do question number 3, which is probably kind of on the long side, in the next video. Hope you found this helpful, and good luck with this.